Good morning. I hope that you are doing well. For one, I'm doing fairly well. I've got a lot going on nowadays, and yeah, it's been a busy time. And this week, saw a lot of frustration. Again, Ball Butler is there's just this throwing a ball, getting a robot to throw a ball is a lot more annoying than I ever would have thought it would be. Even after having gotten Jugglebot working and like being able to throw a ball, I I don't know if it was good luck or John's careful stewardship or some combination of both of those, but Jugglebot it just kind of like it obviously had I had difficulties getting that like throwing mechanism to work, but like it does just work now. Like it works fine. And I don't think I realized how many things have to work well together for that to work. And going through this process again with Ball Butler has really made me realize how many things can actually go wrong here. And yeah, how much needs to go well for it to actually work. And yeah. So I'm keen to the TLDR. I guess you've seen the thumbnail and the title of this stream, so you obviously know that throwing is working now. But I've had to make a compromise that I didn't really want to have to make. But we'll get there when we get there. First thing is that Roz is back, probably. I have been umming and ahhing for probably as long as I've been like seriously working on Ball Butler as to whether I should include Roz as like the main kind of control, like the main brain of Ball Butler, or if I should do something else. And yes, it's been an ongoing thing, but the crux of the matter for now is that if I do use Roz, then this massively simplifies what the Teensy needs to do. And to show you what I mean by this, I want to go back to my my schematic that I showed off last week. I have links in the description, a link in the description for the GitHub repo for Ball Butler, and that includes all of this schematic stuff. So it includes the KiCad file, so you can open it up and do exactly what I'm going to show you that I'm doing. Or there's also a PDF version of this as well, so you can like scroll through and follow along if you so wish. Yeah, one thing quickly that I just want to mention that I forgot to mention last week explicitly is that this software is designed to be used for making wiring diagrams like this, where you have like electrical connections being shown, connecting different things together electrically. But I'm also using this for programming logic. So for example, in here we have like a function in my program, and this function takes in certain inputs, and these have moved, and it outputs certain outputs. And so these are all, and like these lines, they're not electrical connections, they're just kind of like information flow connections, if that makes sense. I should have drawn more attention to that last week because I just kind of like jumped into this being what I'm doing. I kind of forgot that this is not a normal thing to do. But anyway, yeah. So if we do use Roz here, what this means is that all of the control of Ball Butler, so all of the inverse kinematics and everything that is kind of complicated about the control of Ball Butler will be done on the Jugglebot computer. And then when we send a command to Ball Butler, hey prop guru, it's good to see you too. When we send a command to Ball Butler, rather than last week, you may remember we were sending a command for like throw a ball to this position at this time, and then Ball Butler would do all of its own inverse kinematics and like figure out where it needs to go in order to make the ball end up in that spot at that time. Now, if Jugglebot computer is going to be doing all of that calculation stuff, then what we can do is we can just send the ultimate, like the position that Ball Butler needs to be in for it to make that throw the way that it needs to be made. So this means all we need to send to Ball Butler is what yaw angle it should be at, what pitch angle it should be at, the velocity that it needs to throw at, and the time that it needs to throw. And that's it. And then we can take in that information, and all we need to do is have this nice little system here, which let me not block it with my camera. So all we need to do is take in that throw command. The yaw angle goes up into the yaw loop that I showed off last week, where this is basically just like internally making sure that the yaw angle is correct. And And then we take the throw speed and the throw time, and then as soon as it's the right time to begin the throw, then the trajectory planner will make sure that throw is carried out. And this stuff, all of this part at least, is identical to what is going on inside Jugglebot. Honestly, all of this is identical to what's going inside Jugglebot's hand, except for the Yaw stuff. So the only thing that's new, the only thing that's different about the teensy that's controlling Ball Butler and the teensy that's on Jugglebot's hand is just the Yaw stuff. That's it. So everything else is the same. So it should be pretty straightforward to implement that on the teensy at least, because I've already done it. I've exactly got that carbon copy already. Yes, John was a big advocate for doing this. Yeah, and yes, he says, nice, that's much better. And Batboy says, I was curious how much processing power the teensy needs for inverse kinematics. Yeah, I feel pretty good that the inverse kinematics could work on the teensy, and I want to be clear as well, the main reason why I am leaning towards this change right now is just because it will make the code on the teensy significantly simpler. For the record as well, if you don't remember what the diagram looked like last week, I still have it down here. This is all of the other stuff that was going on inside the teensy before. I've kind of like copied most of it out. So it was basically like this stuff merged with some of this stuff up here. So like this whole thing was what we were doing before, and now we're just doing this little, just that. However, like this stuff, it hasn't just disappeared. Like, don't get me wrong, this stuff is still being done. Well, a lot of it is still being done, at least, not all of it. But it's just being done inside the Jugglebot computer instead of on the teensy on Ball Butler. And a big reason why I am kind of keen for that is because I am much more comfortable programming and understanding code in Python, which is what I'm doing all of the ROS stuff on the Jugglebot computer. I'm much less comfortable with C++ or like Arduino code, which is what's being run on the teensy. And yeah, it's going to be a lot simpler for me to work through this if it's all in Python. So it'll just be faster for me to get this working. I'm still, of course, my reasoning for why I wanted to have all of the calculations and all of this stuff being done on the Ball Butler still holds. Like, I still want this system eventually to be completely self-contained. So I can just tell it, throw a ball to this XYZ position at this time, make it happen, you figure it out, and it will do it. That will need to happen eventually because I want to have this robot working with me, like throwing balls to me while I'm juggling. But I am happy to... I'm trying to go for like the minimum viable product. You know, just get it done, get it working, and then we can make improvements in the future. Yep. Fluzzy says, currently all the inverse kinematic stuff is in Python, so if computation speed is a bottleneck, it could probably be easily moved to a high performance language. Yes, definitely. I really don't think that the Jugglebot computer is going to have any issue with this inverse kinematics. It's pretty, yeah, I think it should be all right. Rudiger says, I live that sea life because I need to feel something even if it's pain. Yes, I'm feeling plenty enough as it is, so I don't need any more pain in my life. And Batboy says, it definitely makes sense to isolate the teensy to PID and sensor readings and such. Yeah, keep it simple. Yep. So there is one kind of asterisk though on what I've explained so far with this, which is that the yaw angle needs to, like, it needs to have like a solid baseline point where like we have this position is 0 angle, and it's possible that I need to fiddle. I also haven't touched the yaw angle stuff in a couple of weeks because I've been working on the pitch and the throw, but I am pretty sure the only, like, the best way to handle this is that at the beginning, when the system first boots on, we will probably need to send a call and response message from Ball Butler to Jugglebot to say, hey, just so you know, according to my own internal system, I am at this particular angle, like 30 degrees or whatever. And then that will be combined with the motion capture data from the cameras in my room. We will be tracking the, you guys can't really see that. We'll be tracking the position of the lid of Ball Butler, and we can like use both of those together. So basically, like, Jugglebot, it's all wide up, I can't move it. Yeah, Jugglebot will basically say, okay, cool, I can see that you, Ball Butler, are at this particular angle. You need to be 15 degrees around from where you are right now. You need to like rotate clockwise by 15 degrees in order to be at the right spot to make this throw that I'm telling you to make. And then Butler will be able to say, cool, okay, I'll rotate 15 degrees. And maybe we don't need this call and response. I don't know, just talking about this now, actually. We'll see. That's up for debate. Yeah. But at a minimum, we will need this throw command message, and this should be a lot more straightforward than what we were doing before. You'll notice that we don't need to do any kind of like wacky sending data in the arbitration field. Like, that's nice. That's just empty now. We're not putting anything in there. And yeah, so it should be a little bit cleaner. Yeah. Yep. Cool. It'll definitely make the C, like the Arduino code, significantly simpler. Yeah. So I'm kind of inclined to move back to ROS, but we'll see how we go. I'm definitely leaning towards it at the moment. Yeah. All right. And Fluzzy says, I used to use C until I discovered C++, then I discovered Rust, and I'm never going back to C. I've never used Rust, but I've heard good things. But yeah, I don't know. I don't think I'm a programmer at heart. All right. So another thing from last week is that I was trying to use these, what are they called? AS5047P encoder, the magnetic encoder that works off of SPI. I was commenting that I was getting a lot of noise problems and I wanted to fix the noise problems once and for all. And I found these, I actually don't have the box with me right now, but I found these AMT21, they can be 212 or 213 encoders. I've got a link in the description for these encoders if you want to check them out. And these work off of an RS485 protocol, or like a, what is it called? A half duplex RS485. So fancy. Which basically is like a twisted pair of cables, and they both send the same information but inverted from each other. And that way, if this twisted pair gets exposed to any noise, both of those signals will deviate according to that noise together. And then the receiving end can just look at the difference between the two signals, and it basically filters out all of the noise. So it's much, much, much more noise resistant, which is exactly what I want. So I got these encoders and I was wiring them up, and I looked at the data sheet and I'm like, okay, cool. Here is the encoder, and we have these 6 pins. We can see that pin 5 and 6 are not being used for anything. All right, cool. But like, which pin is pin 1? Why do they not just number them? They have so much space over here. They've got so much space all over this to include the number of like which one actually is pin 1, but they don't include that information. I'm like, okay, fine. All right, I guess. They do tell us that we are using this particular connector type. So let's go to the datasheet of the connector. All right, this is a bit messy, but cool. We can see that the connector is I take this diagram here to be looking towards the back of the connector, where you're like putting the pins into. And to justify my belief, this is the view that I'm taking this to be as. And like, that looks pretty similar. Obviously there's a different number of pins, or circuits they call them, but I'm pretty sure that's that view. The other view from the front looks like this, and I'm pretty sure that does not match up with the diagram. So I'm taking this to mean looking from the back. And this tells us that circuit number 1 is the one on the far right, which would mean this pin over here. The one on the far right is pin number 1. And I was like, cool, I'm so clever. I figured this out. This is great. I like went to all the data sheets. I'm such an electronics engineer. Look at me. And I started wiring it up like this. I put all of the pins in to the little connector in here, which are a bit fiddly to do. And then only once I started, I was checking continuity with things. And then I realized that the shell of this, I should have gotten one out, but I didn't. This shell here is metal, and that is connected to ground. And so when I was going through checking connectivity for things, all of them were being flagged on the ground connection. I was like, this is weird. But it was because my my multimeter probe was when I was probing it in here, I was touching the shell just a little bit. And because that ground connection is the same as this ground connection, from that I could figure out, not a dead encoder, John. I figured it out before that, thankfully. Thankfully, as I was probing this through, I was like, oh, hang on, this ground is the same as pin 4 ground. This means I can figure out which pin is pin 4. And it is not according to the diagram over here, which is not the same it's not from the same what are they called, datasheet as this one here, but it's the one that I thought it would have been. But no, it turns out the numbers are just like left to right. Like, just fucking number them. Like, I can do it right here. Just if I just like uploaded this to AMT, I'm like, here, this is an improvement on your datasheet. This actually includes the information that you need to wire this up. Yes, I'm very glad that I was able to figure that out. And yeah, as Batboy and John both predicted, this would end with a dead encoder, but thankfully I did not get that far. However, because pins 5 and 6 are not being used, I had only wired in like the last 4. So like I had wired in what is actually 3, 4, 5, 6. So I had to take out pin 5 and 6 and put them into pin 1 and 2. And if you guys have never done that before, getting the little pins out of here, because they clip in, they've got like a one-way little ratchet thing, getting them out of these connectors is so goddamn fiddly. And yeah, that was basically my first experience with this type of Molex connector. About 15 minutes in, I have to take the pins out. But thankfully, nothing broke, and I have working encoders now, and it actually does work. And there's like very little noise, no noticeable noise problems. It all just worked. Like, yeah, hooking it up to the O drive, that was again a little bit fiddly, trying to just like make sure that everything is in the correct pins. But I was so relieved when I think this is the first time I've ever had an encoder where I literally just plug all the sides in and it just worked. So I guess I'm learning something, maybe. All right. Now for the juicy bits of this week. Getting the hand to throw. This was quite an adventure. Yes. So the first thing that I did, as I mentioned last week, I was feeling good about using capacitors to store the energy that's needed to make the throw, and that way when the hand motor needs to accelerate really rapidly to throw the ball, it can grab that energy from the capacitors and use that to throw, and that way it won't be too demanding on the main power bus. Yeah, Fuzzy says there are reasons why I'm glad my hardware stuff is limited to servers and stuff with easy cables. Yes, yeah, cabling. Honestly, that is a lot. It takes so much time to make cables the right size and like the right pin out and everything. Yeah, it's very tedious. So yeah, with these capacitors, I bought these. This is going to be a bit of a spoiler, but I bought these capacitors off of Amazon, which I don't know if Amazon is different in different countries, but in Australia, Amazon is like really not where you go for electronic stuff. It just has like very little on there. But I got these on there because they had like cheap shipping. And so these are my 4,700, where's the label over here? 4,700 microfarad capacitors. These are all discharged, by the way, right now, so I'm not worried about flinging them around. And yeah, so I started off with just one of them because my calculations actually, I can show you this. My calculations suggested that we only need, and you can pause and read through this if you want to, but the suggestion here was that the end result here is that if we want the power bus to be operating at 24 volts and we want to have a lowest drop point of 21 volts, then we only need 2,000 microfarads. And as I just said, these capacitors that I bought are 4,500 nominally. So I thought, well, cool, okay, one capacitor should be enough. But it turns out that it wasn't, and adding more capacitors had very rapidly diminishing returns. So this is what things look like with no capacitor. And for context here, this top graph is showing the velocity. The middle, why is my eraser stuck? The middle graph is showing the voltage on the bus, and the bottom graph is a bit cut off, but it's showing the current that is being sent into the motor. And this is all of these graphs that I'm about to show, except for the very last one, are all for the same commanded throw, which is me commanding Ball Butler to throw with a throw velocity of 2.5 meters per second, even though they were not remotely close to that, but we'll talk more about that in a sec. So they're all having the identical command. And we can see here with no capacitor, we make the throw, the velocity spikes, and then the voltage on the bus drops all the way down to like a bit under 6 volts, which is like way too low. For reference, the O drives will shut off after the voltage drops below 10.5 volts. So anything below 10.5 volts is not okay. because both the O-Drive Micro and the O-Drive S1 they'll both shut off. So we can't have that happen. Yes, it is a lot of capacitor. Yeah, I don't know if this is actually like dangerous if it's when it's fully charged. I've been careful with it and nothing has happened and it seems fine, but it would be good to know if this is like an actually dangerous amount or if it's like fine. But yeah, nothing has happened so far. So the first, I put on one capacitor and we can see a pretty big improvement. Rather than dropping down to under 6 volts, it's dropping down the minimum at around 8. Like it's not, it should be, according to my calculations, it should be up at 21 volts. So this drop shouldn't be nearly as big as it is in reality, but it's an improvement. And I thought, okay, all right, let's add a second capacitor. And this, I know the scaling is different on these, so it's a little bit hard to compare them easily. But like for one, we can see it goes just above 8. And then for 2, it's just below 10. So it's still an improvement again, but not by as much. And we can keep going. I go 3 capacitors. Again, ooh, we're getting above 10 now. We're getting into the borderline, it's fine territory. And at this point, I realized, all right, now a problem that I mentioned last week was that these electrolytic capacitors have a fairly large, what is it called? Equivalent series resistance. Now, because I bought these on Amazon, there is no datasheet for them, and the Amazon link had like basically no information on them, other than that they are 35 volt rated and 4,700 microfarads. That's it. I don't know anything about the derating profile of these, so it's possible that because I'm running them at 24 volts, they only have like 50% of the capacity that they're rated for. Maybe. I don't know. And yeah, so I've got like no information about what these actually are. So I thought maybe their equivalent series resistance is super high and they're just not able to dump their energy fast enough for the O-Drive to pick up that energy without draining the bus. So I actually don't know where it's gone right now. Yep, it's gone somewhere. Oh no, here it is. Yep. So I also separately bought some ceramic capacitors, which have a much lower equivalent series resistance, and they should be able to dump their energy much faster. However, they store significantly less energy. So what I did is I soldered together these 5 10 microfarad ceramic capacitors, which you'll note this is only 10 microfarads each, where this is 4,700 each. So they have far less energy inside them. However, I was thinking that because they're able to dump their energy so much faster, they should be able to like dump their energy and keep the bus voltage high while these capacitors, the big capacitors, are like ramping up to dump their energy. So my next approach was to use the same 3 capacitors plus these 5 10 microfarad ones. And there's no difference. It did not make a difference at all. So yeah. I don't really know why. I made sure that the ceramic capacitors, all of these were as close as I could physically get them to the power terminals on the O-Drive. But these small ones, these ceramic ones were like these 2 red connections in here, these were like in the power terminals for the O-Drive. So they were like right there, and apparently it didn't help. I also, another thing that I noted here, because these graphs are so annoying to, like these are all just from the O-Drive GUI, and because they're kind of annoying to, like you can't set the scale or anything, and they're a little bit annoying to deal with, I thought maybe I can use my oscilloscope to capture some of this data. But for some reason, when I was doing all of these tests, I had, for some of them at least, I had my oscilloscope connected to it, and I had the measuring terminal, like again, right on the positive line for the O-Drive, and the oscilloscope was not picking anything up. According to the oscilloscope, it was just full 24 volts the whole time. It just did not waver one bit, even though the O-Drive measurements of the voltage on the bus dipped by heaps. So I don't really know what's going on there. I don't, like maybe the voltage drop is not propagating across the bus and this is just like internal to the O-Drive. I don't know if that actually makes sense, but maybe. I don't really know. Yeah, if anyone's got any thoughts on that, I'd be keen to know. Yeah. So I thought, all right, stuff it, like 2 to 3, like we've gotten from like 9.5 volts up to 10 volts, and we only need to be above 10.5. So let's just go 4. I chucked a 4th capacitor on and it worked. And so now we can see that when we're only dipping down to like 23.9 volts. So we are well within like the range that we're happy with. And I thought, why not? I'll just keep going. Let's just add a fifth one. It should be better, but in reality, it's actually not, which is making me think that the 4 capacitor version is like not that helpful anyway. But to basically at this point, it was taking too long to like test, to like solder a new capacitor on, hook it back up, test it again, and I thought, why not? Let's just go like crazy. Let's just see what will happen if we use all 10 of the capacitors. And the 10 capacitors worked perfectly fine, just as 4 and 5 did, for the 2.5 meters per second throw. But as soon as I increased the velocity of the throw, just by a little bit, just up to 2.7 meters per second, all of a sudden we're back down to where we were before, and the voltage drops below the threshold where it where the O drives turn off, and yeah. So even with all 10 capacitors, they are not able to dump their energy fast enough, maybe, or maybe these capacitors are just like shit quality and they just actually don't have enough energy in them to support that high speed throw. But whatever the case is, this wasn't working. And I do have a video to show you in a sec, but I've got one more thing to note. Yeah, I think. I can't remember the exact order of these things. Yeah, but in any event, I noticed that there was very rapidly diminishing returns. And these, actually, I will show you this. So let's have a look at this. So yeah, start off with the 4 capacitors, and we can see what these throws actually looked like. So we have... Yeah, so this is what I was commanding in. I was sending in throw at 2.5 meters per second. The 1000 there is just saying in 1000 milliseconds, you should make this throw. And that gives it enough time to like get down to the bottom of the stroke to make the throw. So I send it off. And that's how high the throw is. Like that little tiny piddly like beep. Unfortunately in VLC I can only go back 10 seconds at a time. But yeah, very pathetic throw. So that's no good. And the 2.7 meters per second that caused even the 10 capacitor version to drop the voltage too much was obviously like marginally higher than that. So that was not working. Yep. Would a higher amp power supply fix this? Maybe. That's actually a very good question. I'm glad you brought that up, because all of the testing that I have shown so far, this is all at 24 volts. And you may remember that my main power supply that I'm using is 45 volts. So, give me one sec. I want to unplug this. So I was using this that I bought also from Amazon, is a converter that converts down to 24 volts. And you can see this has a 20 amp output limit. My main power supply has a 12.5 amp output, and I figure that with this, because it's stepping the voltage down by half, we should be pretty comfortably able to get that 20 amps out of this. So I don't feel that the current is the limit. Yeah, it seems like it should be, because if the current is too low, then we would expect the voltage on the bus to drop when it's like being demanded, because it just needs that much power. But this should be able to supply more than enough current to support these throws, I would think. Maybe not. But yes, so we noticed, a very, very quickly diminishing returns here. So I thought maybe let's just see what happens if we try a higher voltage. Let's try 45 volts. And we can take out this converter and just go straight 45 volts into the S1. Now we can't do this in actual ball Butler for like with the rest of the system being the same, because it's still plugged in. Because the O drive micro that is controlling the pitch axis can only support up to 31 volts. So we can't use 45 in the whole system because of that. One option, my thinking here was like, if 45 volts does work for the hand and we can throw and it all works fine, then maybe the answer is just get rid of the micro, replace the micro with something else, maybe another S1 that can support 45 volts, and then we're good to go. Everything is just run off of 45 volts the same way that Jugglebot does, from the same power supply that Jugglebot does, and everything will just work. maybe. So I wasn't too worried about going to 45 volts to see if this would help. And it did. It was better. Until problems. We had a spin out, so I can show you this. We're around 42 minutes. So I was testing it along. Get the ball in. As you can see, we're increasing the throw speed quite a bit, up to 2.9 meters per second we're able to get to. And this, like, it actually works. Like, it throws quite well. Like, that was a much higher throw than what we were able to get before. And it didn't even throw any errors. Like, we can go again. Look at that. We can just keep doing this all day long. And so maybe we can go higher. Go from 2.9. Let's try 3 meters per second. Now we throw up. I've just paused it. Comes back down. Smacks into the hand. Now, of course, Ball Butler is not going to be catching, so we don't need to worry about it actually being able to do these catches. And for all of these throw profiles, I was just doing throw and stay at the top, and that's it. So it shouldn't, like, the fact that the ball smacked into the hand, I think what happened here is, I do want to unplug this. Yeah. I think what happened here is that the spool, actually, no, I'll show you in the CAD. It's way easier. The spool that, sorry, let me just get this open. While I'm opening this, actually, there is a link in the description for this CAD as well, if you want to check it out. It's on Onshape, it's free, you can copy it and do whatever you want. Alright, and a look at comments as well. Is it worth doing a test to verify the power supply delivers 20 amps? Maybe. Yeah, because it is a dodgy Amazon one, so it's possible that it is not actually as good as it says. Batboy says, have you tried like a short, maybe 50 millisecond speed ramp? Yes, so that's a good point. I should show... I'll try to remember to next week to show the actual throw profile in detail. I don't have an easy way to show you that right now, I think. Maybe, unless I still have this on here. Yes, okay, yes. This is what the throw profile looks like, generally speaking. Yeah, so we do have like a ramp up period where we have constant velocity, and then we hold the velocity for a small amount of time, and then the velocity goes down while we are approaching the very top. So like this point here is like when we throw, and then this is for like a full profile, so like a throw, a pause, and a catch. So Ball Butler is only doing like this first stuff. So all of this stuff is nothing. That doesn't exist. So we do have like a ramp up. Yeah, if that's what you meant by that. Yeah. Yeah, so I think what happened is when this ball was thrown up and then it landed down and smacked into the hand, I think because this spool is just 3D printed for now, it doesn't have a very strong connection into the motor. And so I think when the hand smacked down, it caused this to like disconnect from the motor shaft essentially, at least a little bit, which caused the encoder to spin because the encoder is connected to the shaft well enough. So I think what happened is that the ball smacked into the hand, caused the shaft to spin a little bit without the motor spinning, and that made the O drive go like, what the heck is going on? The motor hasn't moved, but the encoder has moved. Something is off here. And we got a spin out error, which normally shouldn't be too bad. Normally you just clear the error and off you go. But I didn't realize that had maybe happened. And I thought, okay, like I can just clear the error. It seems to be moving around pretty fine. The string seems tight. Let's go again. Let's add another throw. Clear the error and do it again. But I didn't check the spool, and maybe I should have. And I don't even know exactly why this happened, but you can see here, if you're paying very close attention, you can see these three graphs here. We've got the velocity, the voltage on the bus, and the current. And notice, as soon as I sent that command, I'll go back 10 seconds. As soon as I send this command up here, you can see I'm loading up through 3 meters per second. Boom, current spikes, motor hasn't moved. I'm sitting here thinking what's going on until very quickly I realize, oh crap, this thing is smoking mega. It was well cooked. This is a very well done motor. Where is it? This one. This still smells now like a day later, and there's actual like proper burn marks between some of the phases, like some of the wires in there. It was, yes, a lot of the magic smoke got out. Like looking from the back, I kind of wish the camera was around the back instead of around the front where it is here, because like this whole chamber, like this whole like space back here was just like full of smoke. It was not good. Yep. Did not love that. Yes. Yes. Not good, not good. I did think, like, in the past, I have had these motors smoke, like, not nearly that much, and I have had them smoke, and I've been able to keep using them afterwards, so I thought, maybe the smoking wasn't that bad. Like, it was a lot of smoke that came out of that. But I thought, maybe it's not so bad. And I ended up, I think this is a little bit out of order. I think at this point I was still like, what the heck is going on? And I realized that I have my fancy thermal camera, so I can actually use that to scope things out a bit. And this was like 2 minutes later by the time I finally got the camera all set up, and it was still measuring like 60 degrees. Also, I noticed that the Teensy is running quite hot, which is interesting. I wasn't expecting it to get to like 40 degrees down there. But yeah, the motor was up at like 70 or something degrees. Yeah, you can see it's even like heating up the string as it's wrapping around the spool. It's pretty toasty. Yeah. I did give it a chance to cool down a little bit, and then I decided to try it again to see if the motor was still alive, but no, that motor is well dead. And yeah, after trying it again, it got up to like 86. So, yep, that motor was cooked. We got a lot of smoke, and then... Okay, so at this point I realized, all right, the motor's obviously cooked. I'll have to replace the motor. That's a bit annoying to do because I've got to restring the thing, but like it's not so bad. I went through that process, restrung it, got the new, like a brand new fresh motor in there. And then when I was trying to run it again, all that I would get is unbalanced phases. And I was using the same O drive as I was before, the S1, that was controlling the motor that got fried. And with a brand new fresh motor, but for some reason, every time I tried to start the motor moving, I would get these unbalanced phases warning. And this took me a long time to work through. And eventually I thought, okay, maybe I'll try a brand new O drive to see if it's the O drive problem. Like maybe the O drive got broken somehow as a result of this motor getting like super, super cooked. I try the new O drive. The new O drive and the new motor works perfectly fine. No issues at all. It's all hunky-dory. Go back to the old O drive, doesn't work. Unbalanced phases. I was scratching my head for so long and I was so worried that this O drive was broken because I only have 2 of these O drive S1s and they're kind of expensive and they're kind of hard to get in Australia. So I was really just fingers crossed that it wasn't the O drive that was broken. After a lot of deliberation and trying to figure out what was going on here, I went to the O drive Discord, contacted them there, and the guy Solomon pretty quickly figured out that there must have been some residue that was left behind. So when the cooked motor got cooked, the wires also got quite hot, as we just saw in the thermal camera pictures. And there must have been some kind of residue left behind, like a burnt residue left behind from the wires where they contacted the O drive S1 power terminal, like the phase terminals. I opened it up, I can't see anything. All of those terminals look completely clean to me. But for some reason, that must be the case because if we increase the current that the O drive uses to control the motor, especially during the calibration process, then it all works completely fine. So with a slightly higher current that's able to like blow through whatever that residue is, it works. So the O drive isn't broken, there's just like a bit of gunk on the terminals, which is crazy. I'm every time I go to the O drive guys to ask for help, I am amazed by how much they know about this stuff. And I'm also amazed at like how many things can go wrong here. Like I would never have thought that could even be a thing, that like a high temperature between the 2 metal contacts would leave some kind of residue that would affect all future connections on there. So much can go wrong. Yes. And at this point, I realized I have gone too deep. This is too much. It relies on too much going perfectly well for this to work. And I took a big step back and I thought, all right, I just want the hand to throw. let's let the aesthetic demands that or requirements that I have for the project, let's let them relax just a little bit. What else can we do to make this throwing a lot easier? The easiest option is definitely make the hand have give the hand a longer stroke. So that's why we have now, you might have noticed, this guy is quite a bit bigger than it was before. So this is probably what I'm going to end up going with, where we have it's the same stroke length as Jugglebot's hand. Actually, it's a full 350 millimeter linear rail, and yeah, it's definitely not the same form factor that I was imagining it would take. I don't love the aesthetics that this brings, but it works, and yeah, that's all that matters. So I have a video as well. Now, unfortunately, I can't show you this in action because I also burnt out this motor. So it's currently not working. However, it does work, and it actually works quite well. So I didn't actually record when the good throws are on here. This has been a very busy week. All right, let's see what that was. All right, so yeah, I started off, as with all these things, I started off going very slowly, and then I worked its way up. Yeah, so we go slow throw, and let's skip ahead a bit, we can speed things up. All right, ball's gone, something happened. Look at that. So good. So good. That throw did throw an error. You can see, if you're paying very close attention, on the wires near the hand down here, you can see the red light glowing from the O drive. So that did throw an error. So we can see here the green flashing light, everything's good. We throw, I think it smacked into the end stop at the top, and that caused some kind of error, and probably spin out error. And yeah, I think that was actually the same. Yeah, that actually might have been the same problem now looking at this, because when I tried this again later, we smoked out. Let's see how that went. Okay, so it's definitely able to do at least one more. Yeah, but at some point I pushed this a little bit too far, and again, the motor let out some of its magic smoke. There we go. Out it goes. Yep. And I believe that these smoking problems are being caused by the spool being poorly attached to the motor, and that's meaning that when the motor starts to try to move, the encoder's not moving at the same time, and the O drive's like a bit confused about what's going on. And I think that's what's happening. I think. Rudiger says, I now see why you're making a juggling robot you can't even catch. Yeah, all right. Have you considered using a drone ESC and just reading the encoder separately on the Teensy? I actually have never used drone ESCs before. I've always seen them being very, what's the word? Like rudimentary devices, I guess. They seem to not be able to do a whole lot, and I'm concerned that if I do something with I'm concerned that I won't be able to control it precisely enough, essentially. That a lot of, like, in drone situations, all you care about is the velocity, right? Like, you can just say, I want to have, I don't know, a velocity of like 3,000 RPM, and as long as it's within like 5% of that, it's fine, doesn't matter. But for my case, because I need position control to be very precise, like if this overruns by like half a revolution, it's going to break itself. So because I need such fine control, I'm skeptical that a normal, like a drone ESC will be able to do this, I think. Again, I haven't used them, so I don't actually know if there are ESCs that can do position control. If there are, I would love to know. But the O drive definitely seems... The O drive's a very, very capable device. It can do a lot. Yeah. Yes. All right. So, yeah, we have... I should have done this in a different order, but we do have some miscellaneous problems as well. I've got the next... I'll talk about the lid one in a sec. So, yeah, one interesting problem that I think is also contributing to these smoking problems is that if the system is not tightened perfectly correctly, then there's a lot of drag in the system. So I can show you this guy and this should have audio that you can hear. We've got a 56 minutes. Yeah, so I had this all connected up, and then I realized that like this is making a very funny sound, and hopefully you can hear it. But I basically, yeah, I don't know, hopefully that's coming through. It's such a gross sound. It's like a very like grindy like sound. And then all I did was loosen up the screws that hold the motor in at the back. And all of a sudden, it's a much cleaner sound. And I want to get it to the point where you can see here I'm like pushing on it lightly. It should be, like Jugglebot's hand is at the point where I can drop the ball in and give it like a light little tap, and then the weight of the ball will carry it the whole way down. So as far as I'm concerned, it should be frictionless to the point where I can just tap the ball and it will fall down. Here I've noticed a little bit of clicking sound. You can see it's almost at that point, and just by like adjusting those screws, it doesn't get to the point where it can actually slide down freely. Yeah, so I'm not really sure why that was happening. I think maybe it was due to, because I was thinking maybe where are we? This one. So this is the setup that I had when I was doing this testing on it. So this is obviously not the same as the, like my current plan is still to have this kind of routing with the string in here, which I will try to remember to talk more about in a sec. But just for this testing, I just had a very, very simple setup like this. And I think like this whole system has to be very concentric, right? Because this is going to be spinning at quite high speeds, and it's important that this is exactly like perfectly concentric. So it's possible that when I first installed these two brackets onto the rail, that they weren't perfectly aligned, and that by loosening the screws that are attaching the motor onto the back in here, that was allowing the motor to shift just a little bit to actually make it properly concentric. So that was maybe the answer, but I have also noticed this in other situations before, where if I tighten the 4 screws into the motor too tightly, it like shifts the frame or something weirdly, and it makes the motor bind up a lot more than if the screws are just like the perfect, like just a little bit loose, which is kind of concerning, because that means that if they're a little bit loose, as this thing vibrates, as it moves, those screws are going to undo themselves. So definitely in the actual version, like in the final construction of Ball Butler, I will absolutely be doing these screws in loosely, but with Loctite, so that they don't jiggle themselves out. Yeah, Rudiger says an ESC wouldn't work well for your requirements. Yeah, I'm curious to pick some up, but I if they can only do it, I could be mistaken about them only really being good for velocity control, and if that is incorrect, then I would love to know, because that's the biggest thing that's holding me back from getting some to just have on hand, because I don't really do anything with velocity control right now, at least. I expect I probably will in the future, but it's not really worth getting right now. And John says, agree that magnetic slipping relative to the rotor caused the FOC to be off and push lots of current into the motor trying to run the control loop. That can't slip with impacts. Yes, cool, okay. I'm glad that my understanding aligns with your understanding. Yep, that's good. I was probably like 75% confident that my explanation was correct. Because I was also thinking that maybe if the O drive is trying to power the motor and the encoder is not moving, then it would throw an error. It would be like, hey, I'm commanding the motor to move, but I'm not reading it moving. Let's just like shut off. And this is also, now that I've burnt 2 motors, I only have 10 of these in total. I've already burned 1 at least in the past, so now I've completely destroyed 3. I'm thinking of making a little like graveyard box of like electromechanical components that I destroy in the making of Jugglebot. I can't bring myself to throw this away. Like, it's just this is such an amazing device that even though it's broken, I don't want to throw it away. But yeah, I obviously don't want to keep breaking these, and I will definitely be putting a thermistor in future versions, so that way the O drive can read the temperature from the motor directly and say, whoa, the motor's getting hot. I don't know why, but it doesn't matter why, it just is. So let's power everything off. So hopefully, once I add the thermistor in, we will not be destroying any more motors. Maybe. James, I might have missed it. Did you mention what size conductors you've got between the capacitors and the motor when you're trying to throw? I did not say. That's a good question. All of these wires are 18 AWG, which I know is not really rated for... That was a comment actually that Solomon had when I was talking about the potential for the O drive to be broken. He asked what gauge... Oh, sorry, he asked what current I'm putting through into the motors, and I have set... At the time, I had a soft limit for the motors of 70 amps and a hard limit of 90 amps. And Solomon politely commented that the wires for these motors that they come with are only 18 AWG, which is nominally rated for 14 amps for a 90-degree temperature increase after, I don't know what time interval that's measured over, but yeah, so 70 amps is a lot more than 14 amps. So these wires, like, it's understandable that they were getting pretty toasty. But I don't really think there's anything I can do about that, because as far as I'm aware, I need to be pushing quite a lot of current through these to, like, just in that split second, just while it makes the throw, and then the current can drop and it can cool down afterwards. But it needs to have that super high current just for a smidgen. But yeah, it's possible that, yeah, that was limiting the capacitors as well. I had not thought about that. I'd be curious to know if you suspect that could be a problem. Flyzy says, regarding the motor, I think, if the tolerance is that tight, I wonder if thermal expansion of the material from the heat of the motors and computers could become an issue. Make sure the screws aren't too long and pushing into the windings. Yes, that's a very good point, Batboy. I have noticed that the screw terminal, like where you screw into on here, is, you can definitely very easily poke through and poke into the windings. Now, the windings don't move relative to the screws, only the magnets around the outside move, but I did notice that I have to be careful to make sure that the screws aren't too long, and they weren't, so they weren't poking into the windings at all. Yeah, that's a good point there. Every maker needs a box of shame. Well, I have... My Jugglebot box of shame is getting too big now, to be honest. I need a bigger box. It's currently under my desk here, so I can't easily show you, and I think if I move it, the box will break. But I have like a box that's probably like this big, this tall, full of every single part that I've ever printed with the intention of it being on like the final Jugglebot, and evidently didn't. And now it's getting a bit big. Yes. But I haven't... There've been a lot of, like, very few electromechanical components that have broken. So I'm just starting to build up my collection of those, I don't know, dead bits. Peak current demand, those wires are now resistors. Yeah. You're limited by your input currents. The 70 in the software wouldn't matter. I don't know if that's how that works, Rudiger. I'm definitely not an expert on brushless DC control, but as far as I'm aware, the current that you... Well, I'm fairly confident in this, actually. The current that you're putting into, like, the O drive can be significantly lower than the current that the O drive is putting out to the motor. Don't ask me on the details of that, but I'm almost certain that that is true. So you can have, like... For example, for me, I can have, like, 20 amps going into the O drive, and then, like, 80 amps going out to the motor. Yep. I'm fairly sure that's true. Yep. Yeah, so after all of this, like, it finally works. I'm a little bit irked by the aesthetics that this has now, and I'm, like, kind of worried about my wall, because, like, this here, like, the back of the shelf here rests against the wall that's, like, that wall up there. So I'm a little bit worried now. Where would the amps come from? The O drive's ass. It's funky electronic stuff, man. I'll put a link in the description after this video to the blog post where I have read about this. So give me like an hour or two after the stream and check in the description, and there'll be a link in there. John says, that's right. The motor acts like a buck converter. Phase current is generally higher than input current. Yep. Magic electronic stuff. Yes, I'm a little bit worried that because this arm is so long now, this will very easily be able to, like, punch through my wall. Like, if this is forwards and then the yaw axis starts to turn around, whack. That is, like, inside the wall now. So I am a little bit nervous about that. I don't love that that can happen. But, yeah, it is what it is, I guess. But one thing that's kind of cool, I've been thinking about like more about the ball loader, like how we're going to get balls into ball butler. And I think that because now that this is very tall, it's made me realize that after ball butler throws, the hand is going to be right at the top. So it would be kind of cool if we have the hopper that's holding all the balls be also right at the top. And that way it's very hard in Onshape to get these mates to work nicely. But it'd be cool if like it's over here, it's angled like this-ish, because like Jugglebot will be like down here. It's over here, it makes the throw, pitch axis pitches back up to be vertical, and then this can just like spin around, just go like bloop, and like click into like a little lever here, and then drop the next ball in. And then it will be good to, the hand will go back down, and then it can make its next throw. So I think that will work quite well. And that way all of this like hopper stuff is out of the way, and there's no real risk of hitting it in normal operation. I think you're going to stare at it enough in CAD that it will look normal. Yeah, maybe. And Fuzzy says it looks kind of sweet with a longer arm. Yeah. Yeah. I mean, it is what it is. I'm going to have to get used to it. Yes, and James says you can trade voltage for current, but that's pretty much a hard limit. Yes, the power is definitely, like, I definitely agree with Rudiger's statement before about where would the power come from. Absolutely. You can't magically generate power from nothing. Like output power cannot be greater than input power, but you can trade voltage and current within that. I'll still put a link in the description though for that blog article, the blog post. It is like very interesting. It goes into all the detail, but I haven't remembered it. Yeah. Yeah, so I think that this will work. However, okay, what I wanted to say before is that because we are now going to a longer stroke, this is not, as I think with all robotics things, and honestly like a lot of like moderately complex projects, you can't just change a thing in isolation and expect it to not have any run-on consequences for other things. So increasing the length of this stroke is helpful because it makes the throw possible, because now we have a lot more time to accelerate over. If that wasn't obvious, that's why this is way more helpful, because we can accelerate for much longer time, so we don't need to push quite as hard while we're accelerating, and then we have a bit longer as well to decelerate at the end. So yeah, it's good in that regard, but it does have other implications, like, for example, being able to smack into the wall. Bit of a problem, maybe. But also, because the stroke is so much longer, we now need to spool up a lot more string onto the spool that's actually like doing the actuating of the hand. And that maybe will cause a problem, potentially. As we can see here, the orange line and the white line are the illustrations of where the string will be after it is fully wound, or after it's fully wound in that direction, plus a multiplier of 1.2, because of course, like the string is actually going to be like wrapped around this midsection a couple times, and I actually think that's actually probably worth drawing attention to. Is it something that I've learned over the last couple days while I have been stringing and unstringing this hand again and again, is that it is very important for the string to wrap nicely around here. It's important that the string is already wrapped like at least a half wrap before, like at a minimum, it should be wrapped around half a wrap or more. Because if it's not, if it just goes straight through this hole here, then it can sometimes want to bundle over itself, and then the whole thing just stops working. Like the string has to spool very like perfectly nicely, as you can see this one is, where it's like the string is always like side by side, and that only works if there's like that only works reliably if there's already like a starting wrap to kind of like start that profile, like to start it like coiling next to the other coils. So that's kind of important, and that's part of the reason why I've added this 1.2 multiplier, is that if the because we basically need to account for like some of this midsection to be covered up initially already, and then we'll be spooling on from there. John says you could change to a copy of the Jugglebot hand capstan design that fixes the motor magnet slipping issue too. You're right, because the Jugglebot hand does, like, because we are now using the same stroke as that, we can use the same spool as that. That's a good point. I had not considered that. However, that's using the magnetic encoder, and I'm skeptical that I'm going to be able to get a magnetic encoder to work on this. Like, using the onboard encoder would be great, but the O drive is just so big, and I don't think it's going to fit unless we move to the... Where did I put a picture of this somewhere? This could come back. Let me... I've been thinking more about this. This idea of cutting out the back of Butler's arm thing, like the back of the main ring, wrapping that around like these like red lines show, and then we can potentially do the cable routing in through here, which would keep it very tidy, out of the way all the time. And that would mean that the O drive would be able, like, we'd have a bit more space out the back here to fit the O drive in there. Maybe. I'll have to think about that. James says, have you considered adding tension elements as tendons and using the motor to oppose the tension? For example, grasshoppers do this combined with quick release type. Yes. I'm glad you brought this up. This is... I can't help but think through these last couple days when I've been working through this, how back a couple weeks ago, we were considering whether to use this like electromechanical approach to throw, the same way the Juggler does, or using something like springs. And for example, I think the best idea that I have heard for this so far, some viewer suggested this, I can't remember who it was, but basically to have a latch down the bottom, a string that comes up and around, a spring on the back, and a motor down the bottom that attaches to the spring. As the motor winds up, it stretches the spring and like generates that tension in there. Once there's enough tension to like meet the throw that we want, we can release the latch and then the hand will shoot up and throw. And that way there's no, like we just need to have that single latch, however that works, to hold the hand down. And then, yeah, as soon as that latch is gone, then the hand will throw. Now there are complications with this with regards to like getting the hand back down again. And like I expect it would be a little bit harder to tune to be able to do like perfect, like a particular velocity throw. Maybe that's incorrect, but yeah, I was debating doing that for a while, and eventually I decided to just keep with the same approach that we know works, like using the motor to do the whole throw. But yeah, I have definitely been thinking, like, what does the parallel universe look like where I decided to go down the mechanical route way back then? And maybe that could have worked sooner, maybe? I don't know. Like, there's obviously, we don't have the counterfactual to actually know how that would have gone, but damn if it isn't tempting. But it's definitely, like, I'm too far... I know that the sunk cost fallacy is definitely a thing, but, like, this works now, I guess is a better way to phrase this. This works, and I know that this works, and even though I've had to compromise on the length of the stroke, it is what it is, and yeah, I'm pretty motivated to stick with this now. John has also said there's plenty of space to mount it higher up on the hand stroke. Potentially, but not really, because the hand is now on the outside of the... Let me fix this. This is annoying, having this move. Because the hand is now on the side here, I don't think we can have the... I guess you're saying like up here. Yeah, we could put it up here. Yeah, now that we have all that extra space up there, because before we didn't have any space up there. Yeah, that could work. That would be a lot simpler. But it's going to be so aesthetically unappealing. Why have you got to suggest all these sensible but ugly ideas? James says, it reduces momentary power demands since you're storing energy in the tension. So it sounds like you're suggesting a combination, James. Tension elements as tendons and using the motor to oppose the tension. I'm not... Do you have like a specific instantiation of this in mind? I'm curious to know what you're thinking. Yeah. I do... I feel like the only thing that I will change from this point is probably to add some kind of like printed damper on the end here, like this little end stop thing works kind of well, but not super well, and it's a very sudden, abrupt stop. I think the main thing that I'm going to change here is to integrate probably into this part to have a combination of like PLA and TPU in the same part that has like a bit of a spongy end stop, and that way it'll just absorb that end shock. That's the only thing that I'm imagining changing here, because I know that this works and can throw very well, like well enough for Ball Butler, definitely. Yeah. And maybe to move the Hando drive up higher. Yep. I'll see how I go with that. That's frustrating. That's going to be so ugly, but it will work. All right. Cool. The last thing that I want to mention is that, as I had in the slides, the lid for Ball Butler is now floppy. And to show you what I mean by this, I'll show you the CAD first. Actually, no, I won't show you the CAD first, because the CAD's a bit different. So now I've realized, I think I've showed this off in the last couple of streams, that like there's quite a bit of slack in this yaw axis right now. And that wasn't always like that. Like, of course, if I had put this together and it was this bad, I was like, this is a lot of slop, and this is not good. Like, that means that we're going to have a very hard time angling it correctly. And I've just kind of been ignoring that because I'm not really concerned about the yaw axis right now. And I'm pretty sure, well, I was pretty sure that this slop problem is just to do with the way that I've constructed this. But because I have constructed this the way that I have, I can't actually like get in here very easily to see anything about what's going on in there. So something is probably going wrong. Probably what it is, well, my thinking before was that what it is the motor. See, now in the next version that I print off, we will have this big lid or big like opening section here to check out, so we can actually get in there. But I think what's happening right now is that the this gear is just like slipping on the motor shaft, because this is just 3D printed, and like there's not a lot of bite. There's not a lot of cutout on that shaft there. So yeah, I was pretty sure that the problem was that it was slipping, but now I think that it's actually maybe something else, because I noticed that as I lift this up, I can like lift up that lid quite a lot. Like it is just like not connected on there. I'm not that worried about this, because the reason, like this instantiation of Ball Butler right now, the lid is only actually attached with these two screws here. So there's one like at my two index fingers here and here, and the other two screws that would be there and that are there in the CAD. It's like my newer version has actually, I haven't even updated it properly, lol. In my newer version, I'm using all 4 screws, 1, 2, 3, 4, and all 4 of those go through, how can I show this easily? Here we go. They go through the top lid, through the bearing, which is like this gray part, and then they go into this big ring. And that ring is what is meshing with the motor to drive that yaw axis. Now, in the current design here that I just showed, there are 2 screws. So like this one here is like not attached to the lid. It just attaches from the bearing to the ring to the gear. And then the same on the other side, this one only attaches between the bearing and the gear. It doesn't actually attach to the lid. The reason why I did that was just for that was the only way that I could do it, so that I could actually construct the whole thing and put it all together. But now that I have this opening, this like hinge in here, now I'll be able to construct it where all 4 of these screws go through both the lid, well, all of the lid and the bearing and the gear. So hopefully this won't be a problem anymore. And also the lid will probably also be thicker now that I've had to move all of this stuff up a little bit. So the whole thing should be a lot more robust, and hopefully I won't have this floppy lid problem anymore. I will also make an effort to not... I mentioned last week that this handle, this like... I even call it a handle. This like thing at the back here, this little arch, which doesn't really... I don't think it serves any structural purpose. I'm interested to know if you guys have any thoughts on this. I feel like this sort of structure will work, probably. I don't really know how much it's going to flex, and I'm curious to find out. But anyway, the thing at the back that I have been calling a handle and using as a handle is a terrible idea to use it as a handle because this lid is so poorly attached. I think that's probably why it's kind of like gotten weakened, is because I've been getting in the habit of lifting up Ball Butler just from this, and that's not a good idea, I think. Use a small motor to retract and a large one to tension, and a more elastic cord like braided nylon, something like cook release. Yeah, this is the problem with this, like the mechanical thrower. I think the mechanical thrower is the future of Ball Butler. I just want to put that out there. I am pretty confident that like when Ball Butler is at the stage where I'm using it for myself, I want it to be as small and compact as possible. And I am pretty confident. And also, if it's throwing to me, the throws don't need to be like 0.1 like meters per second accurate. As long as it's roughly accurate, as a human, I'm plenty familiar with balls not being exactly where they're supposed to be, and I can compensate for that. Probably better than I'll be able to get Jugglebot to do that in the immediate future, at least. So I don't really mind if it's a little bit off. So definitely small, like compactness is more important for me, and I am fairly confident that springs and a purely mechanical throwing arm is probably the way to do that. However, it just gets so complicated. There's just so many more little steps. Like, I think that the O drive is doing so much that I can just kind of like pack in a lot of the difficulty of this problem and give that to the O drive, and the O drive will do it for me. But if we're going a mechanical route, we have to do all of this ourselves. Like, there has to be some kind of latching mechanism. There has to be some kind of elastic element. There has to be something to charge it or to like wind up the elastic element. And there has to be some way to to prepare it again for another, to prime it again for another throw. Like, we have to bring the hand back down again. And all four of those steps, like with the O drive can just do all of those. It does the whole thing. But mechanically, you kind of, as far as I'm aware, I've only ever been able to think of like a solution for each one separately. Like, you can't get like one solution that handles multiple of those. And it just means that there's more stuff going on. It's a bit more complicated. Yeah. And for now, as I said, MVP, I just want to get it to work. Yeah, because this is not the main focus of the project. Like, I want to get back to Jugglebot as quickly as I can. So I want to get this working as quickly as I can. Flazzy says, doesn't a longer arm also reduce the angle at which you can throw because the hand doesn't pivot? Because the hand doesn't pivot. I don't understand what you mean by the hand pivoting, but I don't think it should limit the angle of throw. Like, from the simulations that I showed off last week, there was, like, it seems pretty clear to me that if Ball Butler is up on the shelf up there, throwing down to Jugglebot down here, it will probably want to be, if it wants to throw with the lowest velocity as possible, it will probably want to be throwing at a very shallow angle. And that is a big reason why I have shifted the hand to be on the side here, rather than, like, you can see in the current instantiation of it, the hand is on the front here. And this does mean that if the whole thing tips really far forward, the hand can't go down the whole way. It smacks into the lid. But with the new setup, that doesn't happen. So the hand can go the whole way down and gets very close to touching, but it doesn't actually touch. Now, of course, I am fully aware that the ball will not be held in the hand as it is like this. It will just fall straight out. But I'm going to redesign the hand to have like a bit of a scoop so that it can hold the ball at these low angles. I've got a rough idea of what I want that to look like. It's, I mean, literally basically just like this, plus, if I can remember my shortcuts, plus like a little, where is it? All right, I cannot remember my shortcuts. Oh, fuck. All right, I don't know what happened just then. Yeah, basically just imagining the hand with like a little scoop down the bottom here to hold the ball in, essentially. Yeah. Yeah, hopefully that answers your question. James says, if you're scoopifying the hand, I think that would solve all the problem. Yeah, cool, nice. Oh, now it works. All right. James says, put fasteners through that hinge section right near the pinion gear so it can't pull away and slip if the door flexes. Flexes noise, making it look cool, might make performance worse. Hang on. So I think you were saying this door. Put fasteners through that hinge section right near the pinion gear. Ah, I see what you're saying. So James is worried that because this part can hinge away, where the motor attaches here, this part might flex down and affect the engagement of this gear with the big ring. Maybe. I can't say I'm too worried about that though, because this door is only attached onto the top part with just a single fastener through here. So that will probably not be the strongest connection. And I agree that, like, if I was holding this, then I do think that would probably be a potential problem. But if this is on the shelf, like this is not going to be able to hinge to flex down, because like this is going to be screwed down onto the shelf with the 4 mounting holes around the sides. So like that can't go anywhere. It would have to have the lid flexing upwards. Actually, no, it wouldn't. It would. Well, the only thing that would need, the only way that this could flex to be a problem is if it flexed down. It would have to flex down to be an issue, because the bearing is attached onto the outside. So that this bearing is like fixed onto the. No, it's not fastened with gravity. I was going to say that it's fastened with gravity, but it's not, because the bearing is fastened to the outside of the base, which is stuck to the ground. The lid, and also, sorry, the red big gear is fastened to that bearing. Exactly, but you can put it in compression with a fastener and it will prevent skipping. I don't think it's necessary though, because this bearing is attached to the base quite solidly with like 4 screws. I don't think it's going anywhere. That bearing is also, for what it's worth, like I have tried pushing on it like axially, and it's strong. It is well strong enough to, like, it's not going to flex at all under these kind of loads, at least. Definitely not. I think it would break before it flexed. And that means that the only way that this gear can disengage from the big red gear is if the motor flexes down, which it can't do because it's bolted into the although I guess, okay, so this door is actually not bolted down. The door is only, but it would have to go down. It would have to go through the shelf. I'm not sure. I don't think it will matter. Yeah, as it's not rotating much or fast. Yes, I think even if this were maybe a problem in like high load cases, I think Rudiger's on it, and that yaw axis is like the most tame of all of these axes. Actually, maybe the pitch one is, but it's very chill. I'm not expecting to be driving that too hard or too fast. I'm happy for that to go at like a leisurely pace, because again, like because this is going to be throwing down to Ball Butler, like it can only go as fast as Ball Butler can receive new balls. So I'm not expecting this to be like pumping them out extremely fast or anything like that. Yeah. So I guess my general feelings right now about this, I'm honestly mostly worried about punching a hole in the wall with the arm being this long. I can, and I will, and I actually have already, but I'll change it. Set the current limit on this pitch motor, so that way if this arm does hit anything, like for example the end stops or the wall, that it will only hit it with like a little bit of force and will just like stop powering before it pushes too hard. And that will fix any problems where like this arm itself is smacking into the wall. However, that doesn't help if the arm is forward and the yaw axis starts turning around, and then the yaw axis is what causes the arm to smack into the wall like this. If it goes like whack that way, that's just going to hit the wall, and the yaw axis is pretty strong. So honestly, maybe it's actually good if the yaw axis slips under high load, because then it will save my wall from getting damaged. That's actually maybe not a bad idea. Maybe I should actually keep this. Maybe I should, because I now have access in here, maybe this is actually not a bad idea to keep this gear being 3D printed like this, so that it's kind of like a fail-safe clutch almost, so that will slip if there's any like higher loads all of a sudden. I'll have a think about that. Yeah. Yeah. All right, there is one other thing actually, I lied. There's one last thing which I've actually closed right now, which is, I mentioned last week that I have a rough plan for how I'm going to handle the inverse kinematics of Butler throwing down to Jugglebot, and how my plan kind of relies on both of these robots being flat relative to each other, which I still think is a valid assumption, and I'm still going to move ahead with this. And I think, well, I'm pretty confident that if Butler is not flat relative to Jugglebot, like if Jugglebot's down on the ground like here, and Butler's up on a shelf like this, doing that inverse kinematics is going to be so much harder to handle. So I'm just going to assume that both of them are flat. And I had a little bit of time last night, so I was printing some more stuff off to test out this, the longer stroke arm. And while that was printing off, I started having a bit of a think through what this could work, like how this could work. And I ended up with this diagram here, where we've got like Butler, this is like looking from above, we've got Butler here, we've got like some target point over here, and I was trying to figure out like the relationship of all these elements. And I don't know, it's been a little while since I've done like heavy trig stuff, and this got pretty heavy simultaneous equations, like trigonometric relationships pretty quickly. And I was like, I wonder how ChatGPT can go with this. It failed at first, but then I got it to rewrite my question, and then I gave itself its rewriting of my question, which was spot on, and then it worked, and it did it, and it spat out my code, and it's amazing. I love ChatGPT. It is so good. So I've got a link in the description for, the link in the description is actually for like the whole Butler repo. In that is the schematic stuff that I've already shown, as well as this code here, which is called Yaw Inverse Kinematics. And so what this is doing is we have Butler in the middle here. The radius is just like some arbitrary value, so that can change. We can set this S value is how far away, let's see if this works, how far away the axis, actually, this might actually make more sense if I go into the CAD. So if we're looking at this, looking from above, this is showing, if I fix, oops, here, as this arm moves around, what we care about is the line that the ball follows. So if we go, like we care about like this line here. How far is that away from the center of the rotation? And that is what is being shown here. So this line here is like where the ball will travel as it moves along the pitch, if that makes sense. And so we can set how far away that is, so I can change that to be whatever it actually is in Butler, and then we can change the position that we're going to be throwing to. And this will calculate for us how far the circle needs to rotate in order to have this line intersect with this point. And that's what we care about. So we want to figure out how far do we need to rotate this circle so that so that way the 2D plane that the ball will move through will intersect the target point. And it works perfectly fine as far as I can tell. I haven't like run this through like the full gauntlet, but it seems to be pretty good. And of course there's two solutions to this problem, because we like mathematically we could throw like backwards and it would work, but of course physically that's not going to work. So I'm going to need to make sure that when I actually use this, I filter out the invalid solution. But yeah, this is what I was imagining doing, but I just got ChatGPT to do it instead of me, which I do feel a little bit guilty about, but this is just so much faster. And this gave me more time to actually get the long throw arm working. So, pros and cons. But yeah, that's on GitHub in the link in the description if you want to check it out. And of course the the pitch axis stuff, we can use the same simulation that I showed off last week, where I swear I fixed this so that the axes should be scaled to be the same. Oh no, yeah, they are. Yeah. So now they're all the same. So like X and Y are equal now. Yeah, so we can use this workflow, I guess, to figure out what pitch axis we need, and then the last step is just to figure out what throw speed we need. Now, there is a little bit of a complication with this, which is that because the throw point is like out on the arm here, where the throw actually happens is going to be a function of what the pitch axis, what the pitch angle is. Because like if we're up here and we throw from like this point, come on, come down. If we throw from like that point, like that's where the actual throw happens before the hand starts to decelerate, then we're throwing from like here versus if we move down and we're throwing from the same like stroke point, like now if we're throwing like here, now it's like out here, which will probably, well, it will definitely affect like how the throw needs to be calculated. So we will have to compensate for that, which I don't think should be too bad. I'm hopeful that we won't need to rely on any numeric solutions, but we'll see how we go. And yeah, so regarding the yaw axis, Fuzzy says you can always just in software make the yaw axis only move if the hand is straight up or close to straight. That's a possibility. I'm kind of worried about having software only solutions, given that the consequence of this going wrong is a hole in the wall, and I don't really want to add to the number of holes that I've put in the walls here, because like if it's not obvious, I'm renting here and I don't want to get in trouble with the landlord. Yeah, and it's like software solutions like should work nominally, but you know, software can do funny things sometimes. James says a shear pin made of filament. Now that is a good idea. I don't know how that would be implemented though. It'd have to be like in the motor that powers the yaw axis, I think. Where is it? I think the shear, because like this gear is very attached to the bearing, and I don't really want to muck around with that too much. I don't know where a shear pin could go. I do love this idea. I think just having the gear, having this shear, I think that should just work. Yeah, attaching the gear to the motor. Yeah. Yeah, but then like where? I don't know. I'll have a think about that. I think that having this be 3D printed, I think should work. Or actually, probably the best thing would be to have having the teeth be made of some, like maybe 3D printed, but out of like a really strong material, and then having like a core inside be 3D printed, perhaps. John says you should set command limits. The range of yaw and pitch to toss the juggle work envelope should be pretty narrow. Yeah, but then we have to get it to reload. It has to like be able to move around to get new balls in. Also, by the way, just a very quick thing, I've learned recently that you can press Shift-P in Onshape to hide all of the sketches. That was triggering me for so long. I spent such a long time going one by one, hiding them all. Shift-P will hide all your sketches. So thank you, Martin from the Wintergarten project, for talking about that in one of his videos. Very useful. Yeah, I'm worried about software solutions. I'm not too... I don't know. The more I say that I'm like worried about hitting the wall, I'm not like super worried about it. I think that having some kind of like mechanical stop, like a clutch or like a shear pin kind of idea, I think will work quite well. Yep. Anyway, that is more than enough rambling. I'm feeling good. We're getting there. I think with John's suggestion of having the hand motor be higher up here, like I can... If I don't have this kind of complexity down here, this will make things a lot simpler. Having the ODrive S1, having like this setup, but up here, will definitely work and will be a lot easier. This is going to kill me aesthetically, but yeah, I think that's the go. I actually feel pretty good about that then. That should be very quick to CAD. Like I've already got this CAD here. Yep. All right. Good thinking, John. You're on it. All right. Yeah, I'll do that. That should be very quick to do. I feel pretty good about that. So that means next week we could be in a spot to have all three axes moving together. I'm still like, I'm so torn. It's like literally like you ask me at one point if I think I'll have this done by the end of the month, and I'll probably say no, and then ask me like an hour later and I'll probably say yes. Like, I'm so, like, split as to whether I'll be able to get this done in the next couple of weeks, because I've got so much other shit going on as well. It's like, oh. Yep. Yep. We're getting there. It's close. It's close. I can feel it. All right. Yep. Rodrigo says, nice stream, home slice. Now let's lunch. I agree. It is time for lunch. All right. And last comment, Flazzy says, you should also get the also just do the super low text solution and put something big and flat in between Butler and the wall. Ah, put like padding. That's a good idea. Get like a big foam thing. That's a very good idea. Yep. 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 Thank you. My landlord will appreciate that. That's a very good idea. Yeah. All right. Awesome. Cool. Thank you, everyone. And I hope you found this interesting. And as always, any and all comments are welcome and encouraged. And yeah, good luck with whatever you're doing. I hope it's going well. I hope, yeah. There are so many things that can go wrong, but, you know, we must persist. All right. Until next week, I hope you have a good one.